Yeah, thank you. My pleasure to come down and give the colloquium. This talk will really consist of two parts, talking about the formation of the first black holes in the early universe, high redshift, and then moving down to low redshift, merging together black holes in the presence of gas. That's the plan. I had actually lots of collaborators. I just highlighted the postdocs and students here, who are, most of them are in the job market, so you should read their names. So as I said, the talk really is in two subjects. So the first one is, I want to discuss two things: how the first black holes might have formed in the universe, what were their range of masses, and then how we might diagnose this kind of physical mechanisms that form them. Then the second part is two black holes are often found in nuclei, both at high and low redshifts, and probably surrounded by lots of gas. And then we want to know what happens, both in terms of dynamics and also signatures in spectra and light curves. And again, the key is observationally diagnosing compact binaries. We could continue to three black holes, but and it's in fact quite justified, because I think often there will be mergers which are delayed between two black holes and the third one comes in, but I think in the interest of time, I'll stop at 2. So I want to start by saying that we just submitted a review paper on this first topic with 2 of the former postdocs. Eli was actually here at CCA, and so it involved a lot of literature understanding and searching. And so I want to start by summarizing and kind of review style what we think might have happened in the early universe. So a lot of this is motivated, as you, I'm sure, know, by discoveries of very bright quasars at very high redshift. So this plot here compiles the highest redshift quasars. And there's about 200 of them now beyond redshift 6. And this is the redshift, this is the mass. These were now coming from 5 different surveys, and the most recent ones, and they're all large optical, large angle surveys. So they only see the tip of the iceberg, the bright quasars in large areas, which are rare. So these masses are the lowest. That's from the Subaru survey. And these are actually not masses, these are really luminosities, assuming that the masses are such that these are Eddington luminosities. So these ones, there's some evidence they actually move up. So we're talking about 10 to the 8 to above 10 to the 9 solar masses. And there are about 200 such objects. And then this curve, just for illustration, shows what the mass of a black hole would be, which was born essentially at redshift infinity, at redshift 35, and grew continuously at the Eddington accretion rate. And this would be its mass if it started from 10 solar mass, or it started from 100 solar mass. So this triggered a lot of excitement when these quasars were discovered, because you can see that some of them actually cannot be explained unless you form a very unusually massive stellar mass black hole very early on, and then you continuously accrete at the Eddington rate. So this mostly just tells you that these black holes probably have their origins very early on, and this is probably not plausible to continuously go uninterrupted throughout the history of the universe. And so there are obviously 3 alternatives. Start with a more massive black hole, not a stellar mass black hole, grow faster above the Eddington limit, or merge a lot, and then you can grow faster. Now I just want to say a few more things. So these bright quasars are really bright objects. They're on the 5 sigma tail in the sense of, well, I can more precisely define why it's 5 sigma. Let's not do that now. So the record holder, just everybody has to know, it's 7.54. Discovered in the infrared, and it has a mass of about almost 1 billion solar masses. When I say tip of the iceberg, that's very important. So this is the luminosity function of these quasars. Now it's actually, because of mostly the Subaru survey, it goes to cover about an order of, almost 2 orders of magnitude in luminosity. And the space density is very, very small, and even here, so few per cubic gigaparsec. Now, if you compare this to an abundance of dark matter halos, which we have in the high redshift universe, which I'll talk about, this a few times 10 to the 7 solar mass halo, the redshift, even before this 10, it's about 1 billion times more than these. So it's actually, if you want to think of tip of the iceberg, these objects are super rare. It's really not the full tip of the iceberg. This is just the tip of the iceberg. The masses are important. They come from real estimates. Many of these quasars actually have line widths. So you can estimate the black hole masses from the widths of the broad lines. Some of them we don't have that, then you just assume they're shining near the Eddington luminosity. They're hosted by very large halos. These halos are sometimes resolved. I mean, the host galaxies are resolved in radio, and you can estimate masses or velocity dispersions. They're very large Milky Way sized halos at redshift of 6 or 7. And they're quite evolved. They have solar metallicity. So, so in some ways, actually this is something I like to say is this subject of the first black holes in the universe, it's not entirely fair to focus entirely on these extremely rare Sloan quasars, because most black holes which we think formed probably don't grow up to be Sloan quasars. So I think it's actually more, let's say, more global interesting to ask a more basic question. What were the masses of the black holes that formed at these high redshifts, and how did they form? So we already know that there are massive black holes down to about 10 to the 5 or 6 solar masses in the local universe, and I'll explain, we think we can form those directly. And of course there are stellar mass black holes, and there's probably in between some intermediate mass black holes, which I'll also explain, form again differently. And I think it's a good question to ask. What is this mass distribution, and what are the mechanisms to form these black holes in the early universe? So you have to bear with me. This is a diagram which shows essentially the 3 different ways we think this may happen. And so one of these is very simple. So the one thing I want to emphasize, that black holes below the masses that are currently observed are probably very old. You can explain, for example, the evolution of the entire quasar luminosity function by assuming you have 10 to the 5 solar mass black holes planted in galaxies early on, and then they merge and grow by accretion. You don't need to form new ones. And the ones we see at the low mass end, they're sitting galaxies which are very old. And this initial mass function of black holes is probably also quite different from the stellar mass function, in the sense that there's different mechanisms involved, and the black hole's actual mass function at any given time evolves a lot, unlike the stellar mass function. But still, it's a useful concept. So there are 3 ways I will go through a little bit. So one is very simple. You have in the early universe, we know that you have a collapsing proto-galaxy. So these galaxies start appearing. These are the first dark matter halos in which gas can contract and cool. And the first ones are called mini-halos. The virial temperatures in these halos are very low, hundreds of kilonewtons per second. And we know they will form molecular hydrogen and cool and turn into originally POP3 stars, which are very massive. And these massive stars, in this sense, not so different from normal massive stars, they leave behind black hole remnants. So we know there will be appearing in the early universe up to 100 solar mass black holes. And I don't want to actually talk too much more about these for now. If you want to grow them, that's a different question. I just want to not talk about that at the moment. There's actually obstacles to growing them beyond their seed masses, because they're born in these tiny galaxies and they eject the gas. In fact, the progenitor star already can eject the gas from their hosts. And also when they merge in the hierarchy of building larger galaxies, they suffer recoil from gravitational wave emission and can be ejected. So they may not grow much until much later in the galaxy formation. Now the second and the third channel are actually very different. So suppose we have a larger galaxy, which has a larger relative temperature, above 10 to the 4 degrees. And so this galaxy has gas, which can activate cooling by Lyman alpha radiation. And then you can ask a question, does this object, and these start appearing, by the way, already redshift 20 or 30, these appear maybe redshift 10 or 15, these kind of larger halos. And you can ask, does this object have prior star formation? So generally speaking, they would, because at the earlier stages, when they were 100 times lower in mass, they form these earlier stars. So if you have star formation, you have metals which were produced by the previous stars, and in this stage, you form what you might call the first galaxies. And those galaxies, the thing I will explain a little in more detail, can end up forming intermediate mass black holes, because they can be quite dense, depending on the level of metal enrichment, when they fragment into stars. And you can have runaway collisions between these stars, which can get you up to 10 to the 3 or 4 solar mass black holes by core collapse in the nuclear cluster. So that's if you had prior star formation. Now, if you didn't have any star formation, which again I'll comment a little more on, suppose there's no previous star formation. Now you have this 10 to the 7, a few times 10 to the 7 solar mass dark matter halo with gas that's not had previous star formation. And then you have to ask what happens. And I'll also explain how you may avoid star formation. But if that's the case, then in principle, the natural way to behave is that you again form molecular hydrogen. And you start to form POP3 stars just like here. And this will be a very dense cluster of stars. And you're back to this route where you might form a black hole because of n-body processes and core collapse in a dense cluster. If you somehow also manage to avoid molecular cooling, then you have a very different situation because the gas remains quite warm, 10 to the 4 degrees near the virial temperature, and will collapse much more rapidly inside these halos. And the idea here, which I'll elaborate, is that you form one single or maybe a few supermassive stars, and these supermassive stars can grow quite large and can give you, at the end of their lives, 10 to the 5 or 6 solar mass black holes. So I realize this is a busy plot, but I hope you follow that there's 3 different physical processes which would be responsible for 3 different mass ranges of black holes forming at these early stages. So I want to actually say a few more things. So again, the stellar mass black holes, I think I won't talk much more about. This one is a very promising and well-defined scenario, so I want to say a few more things about it. So here is a diagram which in principle has nothing to do with cosmology or galaxies. It's just a stellar evolution diagram where you have a protostar. This is obtained in one-dimensional calculations of stellar structure and evolution. And what this shows is you have a protostar and it's accreting at a fixed rate. M dot is fixed. And then this shows how the stellar mass is growing as you're accreting. And this shows the radius of this protostar. And in normal situation, we have something like this. So these are 4 different curves at 4 different accretion rates. So this black curve has an accretion rate of 10⁻³ solar mass a year. So what happens is the star is starting to accrete, starting from 1 solar mass. So this would be, again, some dense core, in our case, in some proto-galaxy. And it's growing, and it's increasing its radius. But then it suffers Kelvin-Helmholtz contraction. So it becomes a normal massive star. It moves to the main sequence after about 100,000 years. And it contracts. And when it contracts, it becomes very hot, and it starts radiating UV radiation. Its effective temperature rises to roughly 100,000 Kelvin. So in fact, here is how we think massive stars limit their own mass. Because once you contract and start emitting UV, you prevent further accretion and you terminate growth. And that's the usual explanation for the characteristic maximum mass of massive stars, 100 solar mass. Now, the interesting thing that happens is when you increase the accretion rate. So the same calculation, you just have a protostar that's accreting at a higher rate. And the trick here is actually quite simple. It's just you want to build accreting mass faster than this protostellar core contracts. And in that case, and actually it's just pure mass conservation. You just keep building an envelope, which is arriving faster than you can contract. So what you see here is that this star never actually contracts. There's this critical value 0.03. If it's above that 0.1 or 1 solar mass a year, this star never is able to contract. Yeah.
How do you avoid forming disks in these stars?
That's so. I don't think I have a good answer. You can actually ask. Well, actually, that's a long discussion. But you could the papers which did this, they assume either there's just accretion through a disk, cold gas, simply mass is added, and you somehow have to avoid spinning up the star. That problem is definitely solved in nature because you can ask the same thing for normal massive stars to some extent.
Right, but they have strong magnetic fields and these first stars.
Yes, so I think unsolved problem.
But also you can have lots of objects that become too massive. They can't support accretion. They can.
So it's not clear how these products. This is a 1D spherical calculation. It assumes either accreting from a disk or a sphere in the sense of how much entropy you add. So if you accrete from hot gas, you actually have two effects. You're adding mass and you're also adding heat. The adding heat is less important, turns out. But the main point here is that if you really accrete this rapidly, then the star never contracts. Its surface temperature, it's like a red giant. It's very red and very large. You see the size is about 100 times larger than the normal massive star. And therefore it emits infrared radiation, not UV. So it never has any reason to terminate further accretion. So it keeps growing, and the end of this star is when it goes to about 10 to the 5 or 6 solar masses. Then its core starts to undergo relativistic instability and collapses to a black hole. And the end result of this is actually that almost the entire envelope at that stage, 10 to the 5 or 6, between 10 and 5 or 6 solar masses, ends up being part of this central black hole.
But is this actually correct that what you call a supermassive star can well realistically be a collection of 15 smaller mass stars, in which case the story does not quite give you such a big black hole?
So I'm just imagining there's a protostellar core and mass is arriving, somehow maneuvers to this small radius at this very high rate. That's all I'm saying. So you don't have multiple objects. This is a single protostellar core accreting at this rate. You can ask the question, is that feasible? Or on the way further out, does the gas fragment into multiple clumps? I'll get back to that. I just want to ask something even more basic, actually, which is, well, okay, so this is very interesting. If you have such high accretion rates, you can form very large black holes, essentially within 100,000 years, so instantly. And, well, the characteristic accretion rate actually depends on the sound speed of the gas that's around this protostar. So just for reference, we can start from low value. So in molecular clouds in our galaxy, which are very cold, the sound speed is very low. And this accretion rate for self-gravitating gas at a certain temperature, it scales like sound speed cubed over g. So it's 10 minus 4, 5, let's say, solar mass a year, very small. So in a Kelvin, how much time you form a solar mass star? In the early universe, we have metal poor gas. So if you take hydrogen molecule as the cooling agent, you can cool down to 100 Kelvin or a few hundred Kelvin. You cannot cool below them. So you have a gas that's warmer than in our star-forming clouds in our galaxy. And then the accretion rate is higher, going up to about 10 minus 3. So that's like this one. That's a normal, massive metal poor or metal-free star. And then if you don't have even molecular hydrogen, you have gas at near 10,000 Kelvin, sound speed is 10 kilometers per second, very large, and you have these large accretion rates. So that's the story. Yeah.
Can you say a few words about what the GR instability is when the envelope's like super large and it's at 10 to the 5 to the 6?
Oh, a few words. Well, it's just there's no stable equilibrium solution in GR, and usually the analysis is done with some polytrope equation of state, and it's just unstable to perturbations, radial perturbations. It's not a new result. It's been known for a long time. I think the new connection here is to connect this to the early universe and accretion rate. So in fact, let's do that. So now the question is, do you have such high accretion rates, and how often you might realize that condition in the early galaxies? So I should just say this is a very large piece of literature. There are many, many papers working on this scenario. Sometimes it's called the direct collapse model, but it's basically what I just described. So the situation where this may happen is these so-called atomic cooling halos that I already mentioned. The virial temperature is 10,000 degrees, and they form at redshift 10 or 15, and the accretion rate is very large. And then if you have conditions where molecules are disabled, there are actually several simulations, including by us and others. And here are two examples. So this shows, these are AMR simulations which follow from cosmological initial conditions, look at such atomic cooling halos in the early universe, and they can start, so this gas distribution, they can resolve down to 1000 AU over here. And this one goes even further. So this bottom picture is 500 AU. So you actually do see on very small scales that this warm gas is still at 8,000 Kelvin or something like that, but it does have angular momentum. It didn't get rid of it completely. So it forms a very small disk, and it does actually seem to fragment to a few clumps. But when you measure accretion rates at the resolution of these simulations, which are, well, you can see from here, is let's say 10 AU. The smallest scale on which you can measure accretion rates, they're very high. Furthermore, there are only a few clumps, and this is so small that the timescales here are super short. So something else you can show relatively easily is that these clumps actually should merge before they evolve into stars. So the timescale, these simulations are generally stopped at this point. If you were able to follow them further, you probably would see these clumps coagulating with the central one, because the dynamic of time is shorter than 10 to the 5 years at this point. Okay. Now, the next question is, so this is a very interesting scenario, but how often does this actually happen? So if you want to, again, think in terms of a black hole birth mass function, you have to know how many are there on this high-end tail. And, well, or another way to ask this, how many times does this not happen because something prevents it? So one would be fragmentation, but I think I won't really have much more to say on that for now, that you already asked about. I think the fragments can coagulate very quickly. There's an obvious other obstacle, which is that this halo doesn't look like this at all, because it had prior star formation and metals, and it looks more like a cold gas-filled mini ISM. And well, to prevent that, there are three ideas. And I should just know the answer of exactly how often this happens, other than that it's pretty rare. It's not very well known. I will give you a number at the end. But there are three ideas on how you might shut off star formation before this stage. So first one is UV background in the universe. So the first stars which form, they start to shine UV radiation. So these are the POP3, normal massive POP3 stars. They emit radiation in the soft UV, and then those photons can actually destroy molecules in halos forming elsewhere in the universe. So that's one idea. I'll say something more on that in a second. The other is streaming velocities. This is very interesting idea for the last several years. We know that baryons, after recombination, develop velocity on coherent on megaparsec scales with respect to the dark matter. So if you're looking at very high redshift small galaxies, the gas actually is got some transverse motion with respect to the dark matter halo, and it makes it hard to actually collect it inside the dark matter halo and can disable star formation. And these streaming velocities are, these are perturbation theory, so they have a Gaussian distribution. And in 2-3 sigma upward deviations where these streaming velocities are large, you can actually postpone star formation all the way up to these atomic cooling halos, not in a typical location in the universe. The third very interesting idea is that some halos which reach this stage, which I show here, are in very overdense regions, and they build up extremely rapidly compared to an average halo of the same mass at the same redshift. Now, building up very rapidly just means if you have collisions so frequently that before it takes some time for the gas to develop molecular hydrogen and to cool down, if it keeps getting interrupted by mergers, then you may never cool down. So this is another idea, that you should look into places where they're overdense and there are halos with unusually violent rapid assembly history, and which disabled cooling and can also provide heating, because during the major mergers between these galaxies, the gas gets shock heated continuously. So, and this compressional heating competes with any cooling that you might have from molecular hydrogen, so that also helps. So I should say, okay, suppose some combination of these effects solved your first obstacle, and then you have this halo and doesn't have any prior star formation. You're still not done, because now this halo is collapsing. It will, even if it had no prior stars and no molecules in it, it's now going to start cooling with Lyman alpha radiation and become very dense, and it can accelerate molecular hydrogen formation, and you can then cool and fragment at much lower densities than shown in these pictures. So you have to actually make sure that molecules are not just suppressed previously, but during the collapse of this gas as well. You also have to ask if there's some prior star formation. This was not perfect. There might be some metals, and what do those metals do that can enable? Those metals can enable cooling to even lower temperatures, and it's even worse then in terms of fragmenting to low mass clumps. And that critical metallicity for this is based on the cooling function, assuming carbon and oxygen, it's termed as 5 solar or so. So if you have metallicity above this, you have to worry about that as well. So let me just see. So I wanted to go into some details just because this is my favorite subject, the H2 molecule destruction. I think maybe one slide is okay for me to do that. So actually the world expert on this is Gemma Walcott-Green, who just left Columbia and is now in Santa Barbara. And the points here to appreciate are that molecular hydrogen, which is really driving this early thermodynamics and whether you form a pop 3 star or a black hole or a supermassive star. So I think that's just amusing by itself. You should worry about one molecule. And that forms H plus E in the early primordial gas. You have electrons and hydrogen. So in 2 steps you can form an H2 molecule. And you can destroy it if you absorb a photon into its Lyman-Werner band. These are just like Lyman alpha for hydrogen atom, but they're levels of the H2 molecule, electronic excited levels. So if you have photons in the universe, which are, let's say, 12 eV, those are very interesting because they don't ionize hydrogen, so they have a very long mean free path. They can establish a background throughout the universe, unlike ionizing radiation, which would carve out local bubbles. So these 12 eV photons can destroy molecules in collapsing halos. Now, the formation rate here scales like density squared. Photodissociation rate is a photodissociation, scales like density times flux. So the critical flux, where you prevent molecule formation, will go like density. So you just have to do a calculation where you take a galaxy spectrum like shown here, a realistic spectrum might have lines, and then you have to look at various hydrogen molecular lines and calculate the dissociation rate. And then at a given density, you can ask how large the flux needs to be to prevent molecule formation. Is that clear? So that's a chemistry calculation. And then the question is, what density should you put in? Well, if there's no cooling, the gas was adiabatic. So you should know the density in this halo, characteristic density in the core. So for mini halos, it's very low. There's no cooling. So the density cannot really get above this value, and you get a critical flux that's actually quite low. This is why it's a promising method to get rid of molecule cooling in most mini halos. This number, J21, don't worry about the units. It's in some units. If you haven't seen it, it doesn't matter. It's some number 0.111, but in the same units, if you want just to compare it to reionization, if you want to emit 1 12 eV photon per hydrogen atom, so that's required for reionization to happen, that would be 10 in these units. So this is a background level that's well before reionization. Okay. Now, when the halo grows above this atomic cooling threshold, then the situation changes because there is Lyman alpha cooling. The density starts increasing because the gas now, it's not adiabatic, it's contracting. So the density rises, and you have to plug in a number that's much larger, 10 to the 4. And that's critical density for molecular hydrogen levels. And then this critical flux is very large, about 1,000 in these units. So that's actually much larger than you expect the background flux to be. So this does require some fine-tuned conditions. Okay, so if you want, again, go back to this galaxy, and you want to assume that molecules are wiped out so that you can maintain this large accretion rate, you have to illuminate with this very large flux. And I think that's basically very difficult unless you have a neighboring galaxy forming at the same time within a few kiloparsec from your galaxy. So I think this actually, I'm going to skip this slide and explanation because that's getting a little late. So there's basically a scenario, which I will skip over the details, where you have two of these halos forming nearly simultaneously, close enough to each other that one illuminates the other, and this target that's illuminated is within half a kiloparsec, and it's synchronized within a few megayears, and then you can maintain this high accretion rate and no molecules. So this is synchronized pairs of halos, and you can actually calculate in an n-body simulation how many times this happens per unit megaparsec cubed. And it's actually rare, but it's not super rare. It's about 10 to the minus 4 per, there's every 10,000 cubic megaparsec, there's one such pair, synchronized pair. So that's actually a small number. So it's about 10 to the minus 4 of all these halos, atomic cooling halos. So it's a small fraction, but it's much larger, for example, than the abundance of Sloan quasars that I talked about. It's 4 orders of magnitude larger. So that's good to keep in mind.
So can the neighboring halo contaminate?
So this is from a paper where we delineated the requirements for this. And this here is the separation of the two halos in space where they form, and this is the way they're synchronized. So if they're too close, this doesn't work because the tidal forces will, either tidal forces or ram pressure stripping will remove the gas from one of them or both of them, right? Because the tidal force will be too large. So you have to be above this. If they're too far, they're separated, then the Lyman-Werner flux is too small. And then this is the line which determines metal enrichment. So the closer they are, the more synchronized they have to be in order for metals not to arrive from one to the other. So that's the reason for this. So yes, metals can be avoided because metals travel at wind speeds, and they take more than 100,000. So in 100,000 years, you actually form this supermassive star. So if in 100,000 years the metals don't cross the distance, you're okay. So this works. It gives you a decent abundance, and I do want to go to my second topic. So I think I'm gonna maybe say one more thing, which is, but just to go back. So in principle, so this term is 4 megaparsec could be a rough number. As I said, there's just this idea. So there are these two other ideas, how to prevent star formation early on, and you're allowed to combine these three. I mean, there will be halos which are in high streaming motions and they assemble more rapidly, and they have a neighbor, maybe not so far, not so close, but still a relatively close neighbor, and it's just not being understood. I do want to say one more thing about, since it's my last paper on SOPH, and also because it's the different scenarios. So suppose there are some previous metals produced by previous stars in this halo, then it's actually quite different. The evolution is quite different. And again, the basic thermodynamics of such a gas is shown here. So this is again just a spherical calculation where you have a piece of gas, it's collapsing, and its density is increasing, and it starts on low temperature, and then it's heating up adiabatically up to this point. So if you disable the molecule formation and there are no metals, then Lyman alpha cooling just keeps it almost isothermal until it becomes completely opaque to all photons, and then temperature starts rising. Now, if there are some metals, so this is from an older paper. For example, if the metallicity is 10 minus 5, then the same thing happens. The gas starts to cool and go to very high density, but eventually the metal cooling will lower the temperature and cause this minimum before it becomes optically thick. And so the idea here is, which has been confirmed with simulations, is that the fragmentation happens over here when the temperature is going to this minimum. So this is a very different scenario. These are clouds where they collapse to very high density due to Lyman alpha, and there they start to lose their temperature, and then now there's fragmentation, and it happens at extremely high densities. So the result of this process is a very, very dense star cluster. And in this paper, we worked out the details of this kind of scenario where you include now, there you have this isothermal cloud. Inside it, you have star formation at extremely high densities. The stars move in this cloud due to dynamic of friction. And then the key point is that the stars can collide. The outcome of such a model is that because this happens at so high a density, the stars actually shrink towards the center, they collide, and instead of gas accretion, it's the collision between these stars that keeps the central protostar puffed up. So it's actually in some way similar to the supermassive star case, except you're not accreting gas. What's happening instead is that if stars delivered to the nucleus and hitting the central protostar, and stellar collisions happen so frequently, faster than the Kelvin-Helmholtz contraction time, that you actually build a supermassive star in the middle from other stars. So you eat, and you can actually eat most of the stars here, and grow up to even maybe 10 to the 5 solar masses. So if you fragment at slightly lower densities, the metallicity is slightly higher, then you become limited, and you still can form a massive star, 10 to the 3 or 4 solar masses, but not all the way up to this GR instability. Okay, so these are the 3 ways to form the massive black holes, and I think I just want to reiterate the points here that I think it's possible to form all 3 kinds of masses in the early universe. These are rare objects, but they should exist. They have their different physical origins, and afterwards, after their birth, this mass function, of course, will evolve because galaxies merge, black holes accrete, and I think it's another subject I just don't want to discuss right now. So I do want to say maybe how you actually. So how the question next is, suppose, well, we want to diagnose observationally what kind of black holes formed, how many in the early universe. The question is how to do that, and I think a good number here to keep in mind is that all the models which involve something that's heavier than a stellar remnant, they go up to about 10 to the 5 solar mass, and they form at redshift 10 or 12. So ideally, afterwards, after this is formed, they can very quickly grow and forget their origins. So ideally, you want to detect black holes of this mass at this redshift. That's the. And in fact, it's somewhat of a coincidence, because in these different scenarios, I won't go through again, this mass arises for different reasons. But you want to have some instrument that can see these objects directly. But let me just throw out 4 ideas which could be useful to disentangle what happens. So the first is this direct detection. LINX is an X-ray telescope which could actually go to about several times 10 to the 4 solar mass black holes at redshift 10, directly detecting them. JWST can do that in some long integration. In the radio, maybe you can see these. So these are hopes for direct detection. Another interesting idea is that these black holes, when they accrete, they emit X-rays. And just like I said about the 12 UV photons, a few KV photons also don't see the hydrogen atoms. The mean free path is very long. So now you have an X-ray background, which partially can ionize the universe. So this partial ionization is actually quite unique to X-rays, which are generated by black hole accretion, not by stars. And so this could show up in the topology of reionization. Maybe you can probe this with 21 centimeter power spectrum, which should be smoother on small scales. Or CM depolarization could help with this, because you'll have a tail of partial ionization to high redshift. And that could be probed by better measurements of the large angle polarization. My favorite instrument is LISA, because LISA is the gravitational wave detector, which will fly in space and actually can go well below this 10 to the 5 solar mass at redshift 10. So if these black holes merge, then it will have several dozen merger events is in kind of standard modeling of the subsequent evolution of these black holes, and the distribution of these mass ratios and the number of events will tell you something about this early black hole assembly. I think another way to go is, which you'll hear about next week when Jenny Green comes to give next Friday the seminar, is that at redshift 0, the dwarf galaxies are the ones where some of these early black holes might still be located. These galaxies are old, so that the properties, the demographics in these low mass galaxies at low redshift can actually also be helpful. So I think I have about 10 minutes. Okay. Well, let me say this, because I think this is also very promising. So a more specific way to diagnose this massive black hole formation is kind of staring at you in the face, because what I'm saying in the previous slides is that you have a galaxy whose mass is few times 10 to the 7 solar masses, and you form in the middle of this galaxy, galaxies in quotes, you form a 10 to the 5 solar mass black hole. So, and there are no stars, or maybe there are a handful of stars. So this is way off the M sigma or M black hole M star correlations when this black hole is born. So the idea is that you should look for and catch these objects before they grow a couple of orders of magnitude in mass and they fall into some big galaxy. So if you find on the sky an object which seems like a redshift 10 black hole, 10 to the 5 solar masses, and there's no galaxy, that would be quite a good evidence for this. And so what we looked at with Eli Wiesbal last year is, well, do you have a chance for catching this object so quickly? And so that's a very simple exercise. we looked at an N-body simulation. We had 10,000 such atomic cooling halos, and then we asked if you put a black hole seed in them and you wait 100 million years, which is roughly when they would grow an order of magnitude in mass, if they accrete at Eddington rates. So after 100 million years, what kind of host are they sitting in? And so this plot shows 100 million years after birth, the ratio of the black hole mass to the stellar mass. So this would be the kind of fiducial ratio in other models where the black holes formed much earlier in stellar seeds and grew more leisurely up to some 10⁶ solar masses and are surrounded by a large galaxy. And most of these, you can see, the black holes still outweigh the stars. So the idea is that, and in fact the sum of them get close to this fit canonical relation, but these are seeds which within 100 million years, they fell into a large galaxy, 10⁻11 solar mass galaxy. But they're still satellites. So you can still resolve your weird object with a large black hole and almost no galaxy from the host, which is offset by a few kiloparsec. So it's resolvable with, let's say, JWST. So that's our particular proposal. You should look for, as a diagnostic of the supermassive star or black hole formation in relatively small hosts, is to basically find a 10⁵ or 6 solar mass black hole, which either has no galaxy at all, even with deepest JWST observations, or maybe has a neighbor offset by about an arcsecond. Okay, that would be evidence for this. So I think now I almost used up my time, and this is the second half of my talk, so I'm not gonna do the whole thing. So maybe 5 minutes. So this is actually, maybe it's okay, because this is a very kind of different work, which I've been doing a lot in collaboration with Andrew McFadden. He actually told you about this about a year ago, I think. But obviously, a part of this scenario, even at high redshift, is when two galaxies merge, they carry black holes, they have gas, and what happens to the binary black hole in the center of this merged galaxy. And let's see, I think I want to I really have to just restrict myself to the main point. I think this is really well motivated question also at low redshift, because we know most galaxies, even at low redshift, have supermassive black holes. They merge, and mergers deliver gas to the nucleus. So even in galaxy mergers at low redshift, we expect these supermassive binary black holes to exist surrounded by gas. And so we're going to flip to our simulations and give you only the punchline. So this again is work that you've probably seen in the past. We've been doing this for a few years. So this is the absolutely simplest thing you can imagine of addressing the question of two point masses surrounded by a gas disk. And actually, well, here's the cartoon version. This is what is the cartoon picture of a quasar. There's a black hole in the middle, and there's a very thin, geometrically thin accretion disk around it. And I'm just saying, well, suppose there's a second black hole. You should do a simplest thing, which is a two-dimensional high-resolution hydro simulations. It's crucial to do a huge number of orbits for this system to settle to a behavior that's quasi-steady state. So we've been doing this, and I will skip most of what I wanted to say and just show you a simulation. So these are 2 point masses, two-dimensional gas disk. This is high density, this is low density. And what happens here is, first of all, there's a large central cavity. That's because the torques from this binary push the gas out in there are no stable orbits in this regime around the binary, but you still see accretion onto individual black holes, which is periodically modulated. Okay, so I think the key points, and you also see the formation of a lump here, which is traveling along the rim of this cavity. So in fact, tends to be two characteristic periods in the accretion rate as a function of time. One is the orbital time here, and one is the orbital time of the binary. And this is a factor of, let's say, 5 longer. So then you can do a lot of things with these simulations. You can measure the accretion rate, and you can discover that it's actually not at all diminished compared to a simulation where you just put one black hole. So that's very interesting, because 10 years ago there was a fear or a notion that if you have a binary, then these torques expel the gas, and you may not have a bright quasar-like object. But in fact, the gas doesn't really have any problem accreting on these two black holes. And it's periodically modulated, so it looks like a periodically varying quasar. And I guess I will show 2 more slides. Is there time for 2 more? So one is, so again, this is the main characteristic. There are a few others from this simulation that you can look for in actual data. So one is obviously periodic modulation of quasars. And of course, we generally cannot resolve these binaries, these sub-parsec binaries, with optical telescopes or even in the radio. Actually, I was going to say that until yesterday, but I don't know if you've seen. Oops. Have you seen this paper on SOPH? It appeared last week. This is an object called BHB 2007. It's a very suggestive name. And it was looked at with ALMA. And this is a binary. And this is one component, this is the other. And this is thermal dust emission. And there are these streams. You can believe me, they look just like these simulations in the simplest regime. There's actually mini disks. This is the ALMA beam. So it's actually resolved. You can even measure the inclination angles. And this object is actually obviously not a black hole binary. Despite its name, it's actually a stellar binary in Barnard 59. I don't know why they called it black hole, BHB. But I think it clearly, and actually in this paper, they never really talk about this. They discuss tumor instability to produce these spiral structures. But I think it's extremely natural and simply a result of gravitational torquing. So I think this picture is nice. It confirms this kind of pattern. And then the only other thing I want to say is about observations. Maybe I will show this one curve. So since Cheng is here, I have to show this as the last plot. So we and 2 other groups have therefore looked for periodic quasars. These are large surveys where you have periodic time domain data, and you can look for periodicity. It's actually quite a hairy project. You have to do statistical analysis of periodograms and see if you have some periodicity which is not explainable by stochastic fluctuations. So you can ask me afterwards. We've done this. There are about 200 quasars now by these 3 groups combined, which appear to have periodicity of the order a year time scale, and they pulled out from large quasar surveys of 200,000 or 300,000 quasars. So there's a lot of debate about whether or not the periodicities are real. And I just want to show you the one example. So this is actually from a Caltech group. This is called PG 1302102. And this is the optical data, which was published originally. And we have been collecting new data on this subject, both in the optical and the UV, together with Swift. And you can see that the additional 3-4 years of data sort of looks like it's continuing this pattern. So generally speaking, you have to be patient and wait and see if this periodicity persists. The other very interesting point, which I think I have to stop and not go into details, but in the UV, it's doing a very similar periodicity. And in fact, we have another explanation for this periodicity, which is not from the hydrodynamical fluctuations, but this particular object is a quasar with a Fourier period, and is so compact because the masses are large that the orbital velocities are relativistic. They are about 0.07 c. So there should be Doppler modulation of both the optical and the UV light as long as the gas is bound to the individual black holes and not some circumbinary gas. But that actually should be the case. So one explanation is that this pattern here is simply because the optical emission is modulated by relativistic Doppler boost. And under that explanation, the UV periodicity should be the same as the optical, but with a larger amplitude because the spectral curvature between optical and UV. So that also seems to be continuing actually. In our Swiss data, the UV and optical periodicity so far seems consistent with this. So I'm gonna stop, and actually this is my conclusions from part 2, but most of them I didn't say. I just put it up here in any case. I think periodicity is just one of the few signatures we can use to look for unresolved black hole binaries. So I'll stop there. Thanks.
Thank you very much. Questions for Zoltan? Can you talk a little bit more about stellar collisions? It looks like a very interesting idea, but I'm wondering whether the turbulent transport induced by these collisions would answer the merge problem.
Oh, right. So you're asking way advanced question. Our approach was extremely simple, which is to ask: is the relative velocity during the collision smaller than the escape velocity from? So the calculation actually follows the two stars and their sizes. So we know the escape velocity, and then we said if the escape velocity is larger than the collision speed, then we assume that there's a new star with the m1 plus m2. In reality, I think that's actually reasonable because people have done calculations with simulations, not for high redshift universe, but in general, stellar collisions. And I think that's a reasonable cartoon description. But they
become very, I mean, in these simulations, this virtual products become very extended for what's called helpful this time, right? And if you don't keep colliding, you can imagine.
yes, I agree. We're thinking some more. I think if it cools faster and contracts, then that would change the story.
To go back to the plot you had right at the beginning of your talk of sort of the distribution of redshifts and masses. Then, right, this seems pretty predictive in terms of what we should or shouldn't be seeing at redshift 7 to 9. Right, that, you know, we start seeing a bunch of, I mean, right now the cutoff at redshift 7 or so is mostly observational.
Yeah.
Right, it's just shifting the infrared.
Yeah.
So with JWST, you know, eventually we'll cover enough area. If not, we'll have to wait for W first to cover the area. If there's stuff at, you know,
Yeah, if there's
things there would be really problematic. And, you know, if I squint a little bit, I might believe that things are following broadly, you know, that at redshift 7, the things are a little less luminous than redshift 6. I'm not sure if I should believe that. You know?
well, that's actually better on this luminosity function. This is the 7. There are only 5 objects, so we don't have a luminosity function. At 6, it's actually
things have grown from 6 to 5.
Yeah.
But as we get more points, it's, you know, this basic model that you've assembled things at redshift 12 and they've grown is pretty predictive at redshift 7, 8, 9.
I think so, and I think if you find 10 to the 9 solar mass at redshift 10, then that becomes very hard. You can start thinking of the more exotic scenarios where you have even larger starting masses.
One last question.
Yeah,
Wine.
you mentioned that the low mass seed scenario has some problems with ejecting the black holes, and then this high mass scenario is rare because of the conditions. So do we have a problem explaining black holes like in our Milky Way in the present universe at 10 to the 6 solar mass?
So I think if I think Milky Way kind of galaxies have a, what is the space density? Is it roughly 1? It's higher than 10⁻⁴, so 10⁻². So I think that's extremely difficult to get that number with these more massive seeds. So I think there are two ways to explain that, and actually one opens up an entire caveat to everything I said, which is, so I think one way is to somehow manage to form extra ones with growing the stellar seeds. The other is to have this very high accretion rate and massive seeds continuing and happening even at lower redshift, and then forming many more. So I don't think either of them are 100% excluded. In fact, one musing about the second one is that we actually know that if you look at quasars, mass is flowing into them at rates of several solar mass a year, right? So we know that nature can actually deliver gas at this rate, even when there's high metallicity. The question, I think nobody knows the answer, is, but if there were no black hole there to begin with? So the naive argument that if you have metals, it cools the gas and the sand speed is very low and you can't bring in the gas at high rates, that's actually spoiled in the quasars at redshift 2, because they shine so brightly and their accretion rates are high. But there's already a large black hole. So the question to be answered is, suppose you remove the black hole, can this kind of extremely large accretion onto a tiny region happen in a massive galaxy with no black hole? Maybe somebody in the room knows more on that than me.
All right, I think we should stop here, but please keep asking questions over wine, and let's thank Zoltan again.
Thank you.